So I've opened up this data set here. So what we're looking at is a STEM spectrum image. So this is actually a compound data object. So it's got lots of different data kind of all in one object. So if I click on survey here, we can see the ADF survey image for this sample. So this is a fib section cut from a STO, so strontium titanate, barium titanate bilayer that's been deposited on a silicon substrate. So the silicon substrate is over here on the left. Then we have the STO layer, which you can kind of see in this dark gray. And then the lighter layer to the right-hand side is the barium titanate. Okay, so that's the survey image. You can see then this is the scan, so that's the ADF signal from the spectrum image. So this is the spectrum image region. It's dual EELs, so we have low loss, high loss, and we also have EDS data. So I'm just going to jump onto the high loss data set. Right click to get the toolbar up, and then we're going to use a picker tool and extract some spectral data. So what's kind of cool with these compound data objects, we can actually show multiple things at the same time. So if I choose to show the low loss, you can see that we have both the low loss and the high loss. I can even add in the EDS as well. So EDS and low loss, EDS and high loss, yeah. But let's concentrate on the EELS data for now. So the first thing we probably want to do is just make sure that 0 is at 0. So it's kind of not. So I'm going to go down to a smaller picker ROI, draw an ROI over the zero loss peak, go to the SI menu, align SI by peak. Selected peak appears to be the zero loss peak, but it's currently at 0.36 EV. So it's asking us if we want to make that 0, which I do. So I'm going to say yes. And then we're going to say yes again. And then we end up with the processed data set. So I'm going to say no, I'm going to close that. Now I'm just interested in looking at this aligned data set. So I'm going to close down this other stuff and just look at STEM, SI, TI examples processed. Okay, so I'm wanting to primarily focus on the titanium L line. So or the L line. So you can kind of see that's the L23 edge in the BTO, so the barium titanate. And then you see some quite, big-ish changes in fine structure when we compare the STO and the BTO. So what's kind of interesting with these like transition metal edges is that we have kind of two primary lines, so L3 and L2. And then in some instances, you get what we call crystal field peaks. So you get splitting on the L3 and the L2 line. And this kind of splitting here, this kind of splitting energy is indicative of kind of the local crystallography. So we could expect to see differences if we had kind of different like symmetry, so tetrahedral or octahedral, or maybe the nearest neighbor distance changes. So this kind of crystal field splitting energy, kind of the difference between this peak, or this peak, and this peak is something that could be useful to measure. So that's basically the goal here. That's what I want to try and do with nonlinear least squares. So the first thing we need to do, obviously, we made sure our energy scale was correct. That was important. If we're just interested in these peaks, it would also be helpful for us to do a background subtraction. And then it would also be useful for us to do a deconvolution. So let's go ahead and I'm going to use the kind of the shortcut to put a background window on there. And then I want to do a deconvolve, and let's just see. Actually, that's not too bad. So we maybe don't need to do the deconvolution. So what I'm looking for is kind of differences between the deconvolved spectrum, so the pink one, and the edge. So we see some, we kind of expect the thickness here to be fairly uniform because it's a fib section. But what I'm looking for is any differences in basically the green spectrum and the pink spectrum. So the extracted edge and the deconvolved. We're actually going to do I'm going to focus mainly on the L3 line, not the L2. So I see some very small differences with the L2, but the L3 kind of crystal field peaks don't seem to be any different between the deconvolved and the kind of the non-deconvolved spectra. So I probably won't go and deconvolve the whole spectrum image. So let's just do a straight up background subtraction. So let's do our rules of thumb. So a third, this is 150. So we can actually probably go all the way out here. And yeah. Then let's go to the SI menu, extract signal SI. So as we've done previously. So now I have the signal spectrum image. I'm going to move using the slice tool to somewhere where we can actually see the layers. And then because I'm actually only interested in this direction perpendicular to the interfaces, we can do the same thing that we did in the previous kind of analysis lab. We can extract a line profile from this signal spectrum image. So let's go and do that as we did before. I'm going to just, again, tidy everything up. Let's get rid of that. So we right click, add a line profile. Let's try and put it approximately in the middle of the spectrum image. Hold shift, drag to the other side. So I don't think I got that right in the middle, but we can just try. So then let's just use the plus key, increase the integration width. And maybe I went a little bit too far. Yes, I did. Yeah, okay, so I'm happy with that. I'm just making sure that the selected region doesn't go outside of the spectrum image. And it hasn't, so we can go back, right click on the edge, and then extract line SI. So as before, I'm going to move that around a bit so we can see everything. And we can straight away see where the white lines are in the 2D profile of the signal SI. So let's extract some data. And yeah, I'm going to put it down there. So that's what we're interested in. So the STO and the BTO. So I'm going to start off with the STO layer because it's actually easier to fit, or kind of get our fit right here, and then we just need to then verify, as we did before, that our fit's good over the whole data set. So we're going to fit functions to the 4 kind of multiplet peaks here. So first of all, we're going to draw an ROI over the first peak. If you're not already in the analytical workspace, or I mean analytical technique, make sure you're in the analytical technique. So data analysis, analytical, least squares fitting palette needs to be open, and then NLLS. So this data actually works quite nicely if you fit Lorentzians to these 4 peaks. So that's what we're going to do. So go up to the palette, add a Lorentzian. Okay. So we've got 1 there. Again, I've got the residual is on and the total fit should be on. So let's see if total fit appears in a second. So I'm drawing an ROI over the second peak here. Again, Lorentzian. And yeah, so total fit appears once you have more than one. More than one thing. So third one, Lorentzian, nice. Fourth one, Lorentzian. So before we get too far along, in this case, this is a good example of where it is really important to name these peaks, because otherwise we're going to end up with loads of things named Lorentzian, and it's a bit difficult to remember which one is which if they're all called Lorentzian and then just a number. So let's start with the first one. So Lorentzian 1, we can call that L3A. And then Lorentzian 2, I'm going to call, L3B. Okay. Lorentzian 3, let's call L2A, so you get the idea. And then Lorentzian 4, I'm going to call L2B. Yeah, there we go. So they have kind of more useful names now. Okay, so the first thing we want to do is verify that the fit doesn't go completely ridiculous. So I'll show you. So at the moment I have maybe a few pixels here selected. So it might be worth trying to go down to 1 pixel. We can actually use the keyboard here if you select that and then move up and down. So, okay, you can see the fit there is completely nonsense. And that's because we're actually in a region where we don't have the white lines at all. So this is a useful way of saying, okay, which pixel was the first pixel that we can confidently use. So that one maybe is okay. Then it looks like, okay, this now looks kind of believable. There's a bit of a jump over here, so maybe that's not super trustworthy. Well, basically, things we can start to do are move our windows around a bit. Does that look right? And we can constrain parameters as well, as we saw in one of the other lessons. So we'll first of all so it looks like we have a reasonable fit in most of the STO, which is that region there. Let's see how it behaves in the BTO. Does it still? Okay, that looks like there's a mistake here. And then, but the peak tracking for the L3 is actually quite good. So always just think about, like, what is it that you're trying to achieve? So in this example, we're interested in the splitting of this one and this one. So what we're interested in is the fit maximum tracks the true maximum of each peak. So that's really what I'm focusing on. And it mostly looks good. L2 is not really working great with these parameters, but the L3 is working pretty well. So let's see what other things we could play with. So let's go back to this one. One of the things we can do is, if we right click one of the, models, change fit model. So we can force positive amplitude. So in this example, that makes sense. We can also say the peak should be within the ROI, which I think that makes sense as well. So let's do that for all of them. So we want positive amplitude, peak within ROI range. So first of all, peak amplitude, peak, yeah. So see if that makes any difference. I don't suspect it will for the L2. So the L2, again, that maximum still is a little off for this L2A. But the rest is pretty reasonable. So the only other thing I might try here is this one. We're kind of expecting this to just shift. So I think this peak just kind of moves into this one. So perhaps the full width half maximum is the same, and these two are just overlapping and the algorithm's getting a bit confused. So let's constrain the full width half maximum. So basically, if we go to the least squares fitting palette, look at the peak that we're kind of interested in. And at this kind of, for this kind of position here, I want to lock the full width half maximum. So let's go to the full width half maximum, kind of click the little padlock, lock that. Let's go to L2B, do the same. So full width half maximum locked. And okay, so some pixels it's okay, some pixels it's not really okay. So let's, oh, nope. There we go, maybe that's a little better. Yeah, actually, so this has now adversely affected our other peak, which we're interested in. So let's actually just wind back on that and switch that off. I don't think it's helped us. But just kind of for demonstration, you can kind of just see that it's one of the tools that we have available to us there. So, but yeah, okay, so let's just skip over the L2 and use the L3 line. Okay. Yeah, so that's the region I'm interested in. And we get good peak tracking for the L3A and the L3B. So let's just go with that. So I'm just using the up and down keys at the moment with this picker ROI or picker region selected and just kind of going back and forth over the STO BTO interface and just seeing that. And fit doesn't do anything really stupid for L3. Looks fine. So as before, let's go and hit map and we'll end up with a bunch of maps or line profiles. There we go. So unlike in the previous example where we're interested in a peak ratio, here we're interested in a peak splitting. So the maps or like the line profile data here that we're after is the position for L3A. So in my case, it's this AR, and the position for L3B, so AU. So you can see why it's important that we named our data earlier, because we have, in this case, we've got loads and loads of line plot kind of displays, and it would probably be hard to figure out which one is which unless we actually named them. So, okay, so we're going to use simple math again, AU minus AR. So we go to the process menu, simple math, and L3B. So I've got them backwards, so it should be AU, L3B, minus AR, which is the top one. So L3B minus L3A. Okay. And then that's our peak splitting for those crystal field peaks. So you can immediately see where it becomes, we've got our errors where we kind of effectively fit into noise. But it's easy again if we just right click on the fit up here at the top, use a picker tool. I'm not actually interested in this result here, but then we can use the mirror tool. So go to the SI menu, mirror extraction ROI, and this is BD. So it will be the one at the bottom because it's the newest. So BD, untitled. And there we can see very clearly, if we look at this guy here, so the 2D image of the fit, or you can kind of see where the white lines disappear. Or so we can move along. So you've got a very clear change here between the two layers. So we've got a crystal field splitting of around 2.3 EV in the STO and around like 1.9, 1.8 EV in the BTO. And you can also see a trend in a decrease in this energy as we get to the interface. So maybe that's strain induced change in the crystal field splitting energy here, but we'd have to probably look at it a little bit more carefully and just verify that the fit is good up to the interface. But yeah, so that's pretty much all I wanted to show for this example. Just an example of, instead of using fixed references, in some cases non-linear least squares fitting can be used to kind of go beyond what you can do with a fixed reference. Okay, so that's pretty much everything we wanted to do for linear least squares fitting. So we'll move on in the next few lessons onto the multivariate statistical analysis tool.